Hi, my name is Arthur from TentamenTrainingen.nl, and in this movie we're going to discuss an exercise on the topic of the extreme value theorem. This is a topic that always comes back in your exams and is also one of the longest exercises in your exam, which also means you can get a lot of points for this exercise. Many different skills are required to get this exercise right, such as taking derivatives, knowing the extreme value theorem, and applying it onto a certain domain. Let's start with the first question. Formulate and apply the extreme value theorem on the domain from 0 to 2.5. So, in order to formulate the extreme value theorem, you're going to have to know this by heart, and you can do this by reading it from your book and just read it so many times that you know it word for word. You can all find this in your mathematics book or somewhere else, but this is really something that they just want you to know by heart. So if we then apply it, applying it consists of checking 3 steps. The first one is checking if the function is continuous on the domain. To check if it is continuous on the domain, we actually want to check if there are any conditions. And if there are any conditions that have to hold on the domain, then it is not continuous. If there are no conditions that have to hold on the domain that you are looking at, we can say it's continuous. So if we look at this function, we see there are no fractions or logarithms or anything, so we don't have any conditions here. So if you do not have any conditions, we can say it is continuous. So the first thing you want to check is if it's continuous. The second thing you want to check if it is closed. Your function is closed on the domain if the boundaries of the domain are between squared brackets. So check if the domain has squared brackets as boundaries, because this means that the endpoints are included in the domain. In other words, that your domain is closed. So this, you can easily check this by looking at what kind of brackets you have for your domain. Third thing you want to check is to see if it is bounded. Your domain is bounded unless it goes to infinity on one of the two sides. So as long as your domain doesn't go to infinity, we can say that it is bounded. So check if the domain doesn't go to infinity if you want to check if it is bounded. So we can now say that we have checked all 3 of these elements, and we can say for each one of them, is it continuous? Yes, there are no conditions that have to hold. Is it closed? Yes, we have squared brackets. Is it bounded? Yes, it does not go to infinity on either side. So we can conclude then that the extreme value theorem holds on this domain. So now we have formulated and applied the extreme value theorem. So the formulation you should be able to do yourself. For the second question, we have to compute the first derivative of this function. So the function is x to the power 3 minus 4.5 x squared minus or plus 6x. Then if we take the derivative for x to the power 3, we get 3 comes down and the 3 becomes 2, so we get 3x squared minus 2 times 4.5 is 9, and 2 becomes 1, so 9x plus 6, since there's only an x to the power 1 there. So that wasn't too hard. Make sure you're able to perform a derivative of such a function. In other movies we will see more complicated derivatives. But now for part C, we have to find the extreme points and values and classify them. So if we want to find the extreme points of a function, we start out by looking for the stationary points. So stationary points are the first thing we want to find. And what are the stationary points? Stationary points are the points where the derivative of the function is equal to 0. So the derivative, which we just calculated, we set it equal to 0. Well, we take the 3 outside of the brackets and we get x squared minus 3x plus 2 is 0. then we can factorize what's between brackets into x minus 2 times x minus 1 equal to 0, which gives us x is 2 or x is 1. So our stationary points are x is 2 and x is 1. So we know that at these points our original function is not in an ascent, neither is it descending. It's actually flat at these points. So we want to know if we are dealing with minimums or maximums at these two stationary points. So we make a sign diagram of the domain and the function in order to see if we are dealing with a maximum or a minimum at these stationary points. So for the derivative, we make a sign diagram from the factors x minus 2 and x minus 1, since these are the factors that together make up for the derivative. Then we say for x minus 2, it's 0 at x is 2, negative for everything below 2, and positive for everything more than 2. Same goes for x minus 1, which is 0 at 1, negative below 1, and positive above 1. So we can conclude that the sign diagram shows that for x minus 2 times x minus 1, we start with a positive part, since these minuses make up for a plus sign. Then we have 0, then minus and plus becomes minus, 0 again, and we finally end with positive part. Okay, so what can we see here? What do we see here? We see that from this plus and minus sign around the 0 at the stationary point, this shows us that the function is ascending and then it goes down again. So when something goes up first and then it goes down, we know that there's a maximum in between. And the opposite goes for the second stationary point, where it goes down first and then goes up. So we are dealing with a minimum at the stationary point. So this goes for the domain from 0 to 2.5, since we are looking only at the domain which is given to us in the exercise. Okay, so one more time. How do you use the sign diagram to look at your stationary points? Since we are dealing with a sign diagram for the derivative, the pluses and the minuses on the bottom row actually tell us how the original function is moving in the domain. So just by looking at the sign diagram, we know that the original function is going up on the first part. This is where the pluses are in the derivative sign diagram. Then it goes down between 1 and 2. And finally, after it reaches the point x is 2, it goes up again. So without seeing the graph, we know roughly how it is going. Then we fill into the original function, we fill in the boundaries and the stationary points in order to find the extreme values. So now we have the extreme points. We know the points of interest, namely the boundary points and the stationary points. And we fill these points into the original function to find the extreme values. So fill in the boundaries and the stationary points in the function fx to find extreme values. So you always fill in the boundaries as well as the stationary points, because the boundaries might as well be extreme values. So the first point we get is f0, and if we fill 0 into the original function, you see we get 0 minus 0 plus 0, which is 0. So then we get the second point is at f1, stationary point, and this gives a value of 2.5. You can check for yourself. f2 for the second stationary point gives a value of 2, and for the final point, the second boundary, f2.5, we get a value of 2.5. Okay, now that we've found all the extreme values, we need to classify them. We need to say if these values are local minimums or maximums, or if they are global and local minimums or maximums. We can do this by looking at the sign diagram and the graph we drew here. As we see at the first point, the graph is ascending, so at the boundary we have a minimum, and since it's the lowest point of all four of these points, we can say it's a local slash global minimum. Lowest of the 4 points, so it's a local global minimum. For f1, which has a value of 2.5, we know that there's a maximum here since we looked at the sign diagram. So since it's the highest point of all 4 points together with the fourth one, we say it's a local slash global maximum. Do the same for f2. This time we know it's a minimum since we looked at the sign diagram. It's not the lowest point of all 4 points, so it's just a local minimum, but not a local global minimum. It's not the lowest point of all 4, so only local. Then for 2.5, same story as for the point at 1. We have a local global maximum since it's the highest point on the domain, and it's a maximum since it's ascending towards the boundary. So at the boundary we have a maximum. Okay, that was all for this exercise. This is how you should note your answers for such an exercise. So be sure to know how to classify these extreme values. Thank you for watching. I'm Arthur from TentamenTrainingen.nl and see you in the next video. Bye bye.